Till now we have addressed two factors. One was the effect of roughness and another one is the effect of cross-sectional area. Let's recall them before we address normal reaction. The first factor was roughness, where we understood that more roughness will result in more frictional force due to more number of irregularities and more depth of interlocking. Whereas in the second factor we understood that the number of irregularities and the depth of interlocking are acting counterwise. That means they are opposing each other in a way to make area ineffective for frictional force. That means frictional force does not depend on the cross-sectional area. Now let's look at normal reaction. Before we start the experiment, I want to explain what is meant by normal reaction. But I want you to imagine you have a friend who is sleeping on the floor with his hands stretched forward. Okay, so he's sleeping on the floor with hands stretched forward, and he asked you or she asked you to pull her with her hands. Then try to imagine the amount of force you require to pull that person. This time, just for the sake of fun, imagine 3 or 4 people are sitting on the backs of that person who is sleeping on the floor. That means the person is sleeping on the floor and 3 or 4 people are sitting on that person. And then you repeat the experiment by pulling their hands. Now make a prediction. When is it harder to pull? When there are no people on your friend, or when there are those 3 to 4 people sitting on the friend? So one of these is the answer, right? So please think carefully. I guess you all thought that when people are sitting or when there is more weight on the person, it is harder to pull. So that's true, exactly correct. But let's think in terms of normal reaction. What is normal reaction is a very important question. Now look at this carefully. Imagine this is the surface, the ground, the floor or whatever. And on this you have a wooden block or a metal block. The weight of the block always acts towards the center of the earth due to gravitational forces. So weight is acting downwards. If the weight is acting downwards, why is the block not going into the earth? Same question we can ask about ourselves. Our weight is acting downwards. Why are we not going into the earth? Because the earth's surface or the floor is stopping us from going inwards. It is applying a force. And in fact, that force is starting from this surface and it is perpendicular, or in this case it is opposite to the direction of the weight. So the surface is applying a force that is normal to the weight direction or perpendicular to the weight direction in this case. This force that is opposing the movement of the block downward is called the normal reaction. Now let's take a different scenario. Let's say the block is placed on a wall, and since it is on a wall, doesn't matter where it is, the weight is always acting downwards. But this time there is no bottom surface. The only surface you have is the wall surface. Here the normal reaction always starts from the surface in contact. So this surface is touching the block and here this surface is touching the block. The normal reaction would be in this direction. Now let's take another scenario like a ramp. Here the block is in this way. The weight of the block is acting downwards just like each and every time. Whereas this time the surface is over here. So the normal reaction would act in this way. So normal reaction, when you say normal, it's not normal to the block. Normal essentially means perpendicular. It is normal to the surface in contact. For this surface, this is the perpendicular. For this surface, this is the perpendicular. For this surface, it is the perpendicular. Normal essentially means perpendicular to the surface. And this surface is applying a reaction to this weight in a perpendicular direction. That's why we call it normal reaction. Now let's go ahead, and before that, look at these two observation sections. The first one is, we will use only a single block, that means 200 grams on top of our wooden block or the plastic block to observe the spring balance reading. And second time, we will give more force, that means we will apply 2 of them and see the results. So as you guess, with less weight, the object can be moved easily. You will see less spring balance reading. With more weight, the object can be moved with more force. You can't move it with less force. So you will see a bigger spring balance reading. Okay, let's get started with our experiment. Now look at the first scenario where I kept only one block on top of it. It's like your friend sleeping on the floor. Now observe the spring balance reading at which the movement starts. Now I am applying the force, right? Just cross 0.5, it's 0.8. So one more time, at around 0.8 newtons I saw the movement. I want to repeat it. 0.5 there is no movement. That's 0.6 or 0.7. Approximately between 0.7 and 0.8 I saw the movement. Now let's add more weight, like more people sitting on your friend. Now this time, as you have predicted, you should see more reading. Now let's check this. 0.5 newtons there is no movement. 1 newton there is no movement. Around 1.2 to 1.4 newtons I can see the movement. I want to repeat the experiment. 0.5 no movement. 1 no movement. Around 1.2 I see the movement. So very simple experiment. Less weight, the normal reaction from this floor is less, frictional force is less. With more weight, the normal reaction will be more and the frictional force will be more. Let's get back to the board to conclude this experiment. Look at these readings. With less weight, that means with a single block, we saw around 0.7 newtons. With two blocks, we saw somewhere between 1.2 to 1.4 newtons. So very simple, more weight, more reaction, more frictional force. Less weight, less reaction from the surface, less frictional force. Let's put it in form of a table so that we can summarize this result in terms of the irregularities too. So here we will focus again on two most important properties. One is the number of irregularities, another one is the depth of irregularities. So friction can be easily explained or easily understood if you focus on these two factors. One is the number of irregularities and another one is the depth of irregularities or interlocking. The first factor, weight. Weight on top of a wooden block. Normal reaction. Third one, number of irregularities. Next one is depth of interlocking. And last one is the frictional force. First, we use less weight. So less weight will result in less normal reaction. Now, see the number of irregularities. We are using the same surface on the floor. We did not change the surfaces. We used the same surface. We only added weights. Now, with more weights, we see more normal reaction. Now, number of irregularities, does it change? You have 1000 irregularities on this, for example. Doesn't matter how much weight you add on it, the number of irregularities will not change because the surface area is not changing. So you will have equal number of irregularities in both scenarios. Now think about the next factor. With less weight on top, the depth of interlocking will be less. With more weight on top, this extra weight is pushing the wooden block much more into my hand or into the surface. It causes more depth of interlocking. So here the most important factor is the depth of interlocking. So less weight, less depth of interlocking, more weight, more depth of interlocking. So this is the key concept over here. Okay. And lastly, we already know frictional force is less when weight of the object is less, and frictional force is more when weight of the object is more. So this is the key aspect, but in order to understand this, we also need to understand the number of irregularities too. So with that, we are done with the normal reaction experiment. There are two more experiments left out in this chapter. The next one we are going to address is interesting because we are going to work with rollers.